Hi, everybody. Today we're doing a very exciting, one of my favorite topics in calculus, actually, and that's called curve sketching. Curve sketching. So let's kind of look at some stuff that we kind of realize. So if you have a graph, so let's say over on this side, if you notice, the tangents are all positive slope, which also means that and since the tangent is the derivative, so that means that y prime is greater than 0. I mean, y prime is positive. And on this side, if I draw a tangent, they have a negative slope, which means that y prime on this side of the curve is less than 0. It's y prime is negative. And where does it switch? It switches on the tippy top. Switches up here on the tippy top. If it's a smooth, continuous, fully differentiable function and all that, then y prime is going to equal 0 up here. That doesn't have to be the case because you could have a thing where everything's going nicely, then it hits a sharp point, something like that. But just keeping it smooth and simple, that's what often happens. Anyway, we see that there is a kind of a correlation now. I don't know if is correlation right word. Actually, correlation is not strong enough of a word because correlation just means it could be coincidental. This is more than coincidence. This is connected, directly connected. But the point I want to bring out here is that we see also when the slope is positive, and of course the derivative is positive, that's happening when the function is going up. The function is what we call increasing. So y is increasing. That directly corresponds to y prime greater than 0, which means a positive slope, which comes from a positive slope. And when I say increasing, I mean going from left to right. Meaning that increasing as x increases. Means as x travels from left to right, y gets bigger, gets higher. And on the other hand, we see on this side that when here the curve is going down, I mean, right? So y is decreasing. And again, this directly corresponds to the derivative being negative, of course, as negative as x increases. In other words, as x goes to the right, y goes down. Whereas for this part, as x goes to the right, y goes up. So this is a super important rule. Now I drew this, by the way, where I just have one point, the tippy top point where y prime equals 0. But what if y prime equals 0 on an entire interval? If y prime equals 0 on an entire interval, then y is a constant. So y prime equals 0, then y is a constant. And which means if I have a function, if I would have a very simple function to graph, if I have y equals 5, that's 5 right there. So if y equals 5, y prime equals 0. In this case, y prime equals 0 for the entire x along the entire x-axis. So we can see this is a classic case of a constant. That's what we're talking about here. Let's say we have a function y equals 2x squared plus 5x plus 2. Well, let's look at y prime. Y prime is equal to 4x plus 5. Now we want to find the critical points, so we set this equal to 0. And that gives us x equals 4x 4x equals -5, because I brought the 5 over to the other side, and x equals -5/4, which which also equals -1.25. So that tells me that this is a critical point. And let's use the first derivative test. I'm sorry, we're not using a derivative test right now. We may as well. Let's look at what happens. Here's the point, -1.25. So let's take as a test point 0, because that's above, and let's say -2, because that's below. So if I take -2, and this is my y prime, of course, 4x plus 5. I like to put this here. I want you to realize what this line is. This is not a line for y, it's a line for y prime. So I want to see where this function, my goal is to see where is this function increasing, where is this function decreasing. And we're just gonna see, is it positive or negative? Is the derivative positive or negative when x equals -2? Well, 4 times -2 plus 5 equals -8 plus 5, which is -3, which is negative. So my function is negative. Now we're going to plug 0 in. 4 times 0 plus 5, and that just equals 5, which is positive. So that means the function is increasing in this interval and is decreasing in this interval. And by the way, we learned in a previous video that if it's increasing here, it's decreasing. If the derivative goes from positive to negative, and that's a critical point, that tells us this is going to be a min. Yes, I'm combining information we know already. But my point for now that I want to say is that the function is increasing till x equals -1.25, and then it starts decreasing again. I'm actually going to show you a graph of the function, and you'll see what I mean. So let's switch cameras here. Now I have to share. And there we go. This is the function y equals 2x squared plus 5x plus 2. And that's my, if you notice, we could see the function is decreasing on this side till x equals -1.25. Now the function is increasing on that side till x equals -1.25. Okay, let's go back. Switch projectors, and we're good to go. Now we're going to look at this function again, the same function we just looked at a minute ago, and want to discuss concavity. So let's take the derivative of y prime. We already did that. It's 4x plus 5. And now let's take the second derivative, y equals 4. Well, 4 is always, there's no critical numbers. There's no critical number because the second derivative never equals 0. And 4 is always positive. None of that. 4 is always positive. So this function is concave up everywhere. Or I should say, and by everywhere I mean for all values of x. And again, if we look at the graph is going to confirm that. We're just switching the. We actually, if we just remind us, the graph. This graph is concave up the whole time because the cave is pointing upwards. So that works beautifully. Okay, let's go back to where we were. I wanted to do a couple more examples. So let's go here. Let's look at the function y. So as another example, I want to y equals x e to the x. Well, y prime is equal to f prime g, which is e to the x, plus fg prime, which is x e to the x. And I could factor this as x plus 1 times e to the x. Well, the only time e to the x is always positive. E to the x never equals 0. It's never negative. E to the x is always positive and never could equal 0. The only time y prime could equal 0, I'm going to set this equal to 0. And what I'm going to do is I'm going to divide both sides by e to the x, which is never 0. So I get x plus 1 equals 0, and then x equals negative 1. So x equals negative 1 is the only critical number. And let's look at a graph. That's negative 1. This is y prime graph we're looking at. So let's take negative 2 and 0. So negative 2 plus 1 times e to the negative 2 is negative 1 over e squared, which is a negative number. So it's negative here. And let's look at let's look at what happens when I put in 0. 0 plus 1 times e to the 0, that just equals 1, which is a positive number. So I see the function is increasing from negative infinity all the way up to negative 1. I'm sorry, decreasing. And here it's increasing. So it's decreasing from negative infinity to negative 1, and it's increasing from negative 1 to infinity. I'm writing this a little more formally. It's increasing from negative 1 to infinity, and it's decreasing from negative infinity to negative 1. And let's look at concavity. So for concavity, I'm going to go to the next, I'm going to look at concavity now. Now, y double prime is equal to, I'm looking up here, y is e to the x plus e to the x plus x e to the x, which gives me 2 e to the x plus x e to the x, which equals x plus 2 times e to the x. So the only time this ever equals 0, again, if I divide each side by e to the x, I get x plus 2 equals 0, x equals a negative 2. The only time the second derivative equals 0 is when x equals negative 2. And let's just check out the concavity. Let's just check out the concavity here. So we're going to draw a number line for y prime, and negative 2 is with 0. So let's check out, you know, 0. I always like 0. And let's just check out, I don't know, negative 3. So when x equals negative 3, I have negative 3 plus 2 times e to the negative 3, which is negative 1 over e to the third power, which is a negative number, which means the function is concave down. And when x equals 0, I get 0 plus 2 times e to the 0, which just equals 2, which is a positive number. So it's concave up. So the function is concave down from negative infinity to negative 2, and is concave up on the interval of negative 2 to positive infinity. And if I was to dare put all this information together and try to graph it, I know that I know that the function has a min when x equals negative 1. Now, if x equals negative 1, let's find the, see, we've established up here, we've established up here that this is a min, because it's decreasing and increasing, so that's a min. And let's find out what y equals. What does y equal at that minimum point? So y of negative 1 is equal to negative e to the negative, negative 1 times e to the negative 1, which is negative 1 over e, and which is about a third, a little more than a third, and a little more than negative a third, I should say. So x is negative 1, and y is a little bit more than a third. That's a min. I know, of course, that when x equals 0, y equals 0, because y equals x e to the x. So if x equals 0, y of 0 is equal to 0 times e to the 0, which is just 0. So it goes through the origin. And I know it's just going to keep on increasing. And I know it's also going to increase on the other side, or I should say decrease, so it's going to go up like this. But when it hits negative 2, it's going to have a change of concavity. It's still going to be, it's still a decreasing function, so it's not really going to turn around, but it's going to become concave down over here, and it's concave up for everywhere else. And let's look at that in a that's a very rough sketch. Let's look at that on Desmos. And here we go. So when x equals negative 1, y is negative 0.368, which is negative 1 over e. And right around here, when x equals 2, I have a sort of a turning point. It just changes the concavity, because the function is still decreasing. That didn't stop. It didn't change. It didn't like start going down. It's still going, or up or down. It doesn't start that, but it changed concavity, and that's a fabulous example. Let's do one more example, and let's go back to our. Okay, and here we go. One more example, and then we're gonna. Okay, so our example now is y equals Let's look at this example now. Y is equal to x cubed minus x squared minus 2x plus 1. All I'm interested right at the moment is just increasing, decreasing, and concavity. I'm going to make a part two, and in part two of this video, we're going to get into a lot of specifics when we sketch curves, asymptotes, and what x-intercepts and y-intercepts and all that kind of stuff. But right now, I just want to find where is it increasing, where is it decreasing, and what's the concavity. So y prime, and I'm going to not do the first derivative test at all. I'm just going to do the second derivative test, which is nice. Anyway, y prime is equal to 3x squared minus 2x minus 2, and y double prime is equal to 6x minus 2. 6x, is that right? 6x minus 3x squared minus 2x. 3x squared minus, okay, now 3x minus this I want to find the critical numbers. So I'm going to set the first derivative equal to 0. And that tells me that the critical numbers are going to be when x is equal to 2 plus or minus the square root of 9 plus 3 times 4 times 2 over 2a, which is 6. And this comes out to be, let's see, this comes out to be when x equals negative 0.549 and positive 1.215. So these are the critical numbers. These are the critical numbers. Now, all I got to do to see if they're maxes or mins, I just plug them in to see if the function is concave up or concave down. Well, y double prime of negative 0.549 is going to be, let me just figure that out on my little calculator. 6 times, it's going to be 6 times negative 5.549 minus 2. Well, it's obviously going to be negative because it's a negative number minus something, so it's obviously going to be negative. So I'm just going to write less than 0, and which means concave down. And y double prime of 1.215 is equal to 6 times 1.215 minus 2. And what does that equal? Well, this is going to be 6. This is obviously 6.6 times 1.2 is bigger than 6. And I'm only subtracting 2, so it's definitely greater than 0, so it's concave up. And notice notice how delightfully lazy I am, in that I see that once I see it's negative, I don't care the actual value. It just cares negative. Here I can see it's positive, so that's all I really care about. Anyway, so we see that it's which means since it's concave down, that means that this here is a max, and this is concave up, so that guy right there is a min. Okay, that's beautiful. Now I want to find where is this function concave up and concave down, and we're gonna set y double prime, which is 6x minus 2. We're gonna set that equal to 0, and that gives me 6x equals 2, or x equals 1/3. So x equals 1/3 is going to be, so if I graph y double prime, and I take 1/3, 1/3 is around 0.333, right? So I'll take my test points, 1.215, which I know already, and negative 0.549, which I also know. So I know automatically that this is concave down, and that's concave up. So our function is increasing. Our function is increasing from negative. This is actually quite interesting. I didn't. I just realized hmm. I never, even though I never did a full first derivative test to see where it's increasing, where it's decreasing, and all that. Um, Logic would tell me is that if I have a max here and a min there, well, and there's no other concavity here. There's no other. It doesn't turn anywhere. So that would tell me that my function has to increase, then decrease and increase, because there's no other way you could have this scenario. So which means was increasing from negative infinity to negative 0.549, and then it's also increasing from 1.215 to infinity, and it's decreasing from negative 0.549 to 1.215. And now you could confirm that with the first derivative. In this case, you did with just with logic. And so we know that this is where it's increasing, that's where it's decreasing. It's concave up from 1/3 to infinity, and it's concave down from negative infinity to 1/3. And let's look at this on Desmos to see how it looks there. So I'm gonna share my screen with Desmos and switch cameras. I'm gonna switch cameras. And pal. So here we are on Desmos, and look at this. So wrong function. So this here, that's the negative 1.549. And that is the story. So our function is concave down in this whole region. It stops being concave down right over when x stops being, what did I say, at 1/3? When x equals 1/3, so it stops. It's concave down until 1/3. Then it's concave up after 1/3. It's increasing till negative 5.49. It decreases till 1.2. Then it increases from that point. And that is it. We are good to go. So that is the end of this video. I'm gonna make a part 2 where I'm gonna go into more depth and detail on our curve sketching. It's been loads of fun, and we'll see you next time. Bye, everybody.